Okay. All right, good. We've got a few more showed up. I'm going to start off class taking my roll call picture. So, you guys aren't near anybody. You can just stay there. The whole point of this is in case that we have to start doing some COVID tracking, we can see if you're sitting next to somebody. You're not, so I don't really care. And best to use proof that you're not. So COVID, as you may have noticed if you look at the news at all, has started kind of blowing up in Utah, particularly in Utah Valley. Fortunately, it's not really too bad up here yet, so hopefully we get at least a few more weeks before things get even questionable. So if you recall last time, right, what do we call these things that I've drawn up here? K-maps. K-maps, perfectly. Car-na, car-no, it's one of the two. I don't know how to say it. Everyone just says K-maps. And they operate on this idea of logic adjacency, right? So as long as the logic is adjacent, we can infer that there is a simplification available. Now, there is one trick to drawing these K-maps. What goes here, right? So this is A, B, and C are 0. This is A is 0, B is 1, C is 0. What goes here for AB? 1, 1. Because that is required for logic adjacency. Because what that means is only one of the bits has changed going next to each other. And then we can go back to 1, 0. Okay, so once we're logically adjacent, that means that there is, as long as they are true next to each other, we can simplify. And we identify the terms that we want to use for simplification by circling any combination of ones as long as there are 2 to the n of them. What that means is 2 of them is good, right? So, just a quick refresher since we went over this a little bit last time, right? This is one good grouping. And because we've done gray code, this and that are logically adjacent. I'm gonna go look at the screen to make sure they can see the red. Okay, I've had some issues with some of the colors in these videos. So then the thing that we want to start looking at in this, once we've done these circles, right? The circles is just the first step part. We know we're trying to get some function out of it. So how do we identify the terms that we're looking for? Well, with this grouping, we want to look at what terms are changing or which terms are, depending how you want to start thinking about it. So what does change in this? Well, C obviously doesn't change, right? Because it's all in this row. So C is 0 here, C is 0 here. And then here, A is 1, but B changes. So B is the unknown in this, right? So let's stick to what we do know. Well, we know it's A and not C is that term, because it didn't change. Or we have this one. Again, C doesn't change, but A does, B doesn't, right? So we have B and C, which don't change, but C is true, B is not true. That is your function off of this truth. Sorry, off of this K-map. In a moment, we'll get to how do you get these K-maps from truth tables, but you can kind of start to see how, hopefully. Remembering that, I'll give you this much, that you're looking for 2 to the n groupings. Just take 30 seconds on your own and identify the circles that you want to make. Okay, what's a good circle to make? Yeah, exactly, right? 2 to the 2 is 4. That's a good grouping. We got to still hang her on. What do we want to do this one? Yeah. So this is important that some people miss. I'm allowed to share. That's not a problem. So, same process. Nothing special. Let's look at this big grouping, and we can see what doesn't change. Well, obviously C changes, right? A changes, B doesn't. So what is our first term? B. Why is it B and not B bar? Yes, because it's true, because of this. Those ones. They're not I's. I should try arrows. There you go. Right? B didn't change. It is true. Therefore, it's B, not B bar. And you'll see that the bigger the circle that I draw, the simpler the term. So we like big circles.
It can also be because it's C is not true and true.
Kind of. That's one way to think of it. If you read through the chapter intro, they go over a little bit more of the why of it. Not very much. We kind of keep it fairly light on the mathematics of why, because this does not have a prerequisite. This course is accessible to all, allegedly. Okay, next term. Who wants to take a stab? What do I write? So C doesn't change. What else doesn't change?
Not A.
Not A.
Not A. Not C.
Yeah, there we go. That's our simplification from that K-map. Now, I want to draw this up here. A lot of times, if you want to be lazy, you don't even have to bother drawing the zeros, right? Now, something to keep in mind, you can start doing stuff with the zeros. We'll get to that. But let's say I'm worried about min terms, right? Those are the ones. I'm not even going to draw the zeros. Go ahead and solve this one, right? There's a couple ways to do it, but I would like you to get me an expression. I'm just going to ask you what it is. And I'm not even going to write those up. You have the answers. And if any of you end up lost or confused on these, make sure to ask questions because these K-maps are important and you are going to see them again and again and again throughout this class. Okay. Who wants to tell me what I'm circling? Yeah, you did one. What am I going to circle?
Can you do the two on the right? Then can you share the one that's like the one on the left and that one? Yeah.
Yeah, so that would be totally allowed. Is there a simpler circle.
Now you can circle the top one and bottom one as well.
Yeah, top one and bottom one. But so you'll see that I only need those two circles because that one gets ones that are already taken care of.
Yeah.
Now we'll get into the importance of that because there is actually a situation where you would want to do that third circle. Right now, for the simplest form, we don't. Did you have a question?
Yeah, real quick. That 2 to the n is talking about how many ones are inside a group.
Yes.
You're gonna have 2 teamwork.
2, 4, 8, 16.
How many-
And they must all be logically adjacent to a neighbor one. So you can't do this 4.
Yeah, so you can have 3 groups.
Well, 3 groups of what?
2.
3 groups of 2. Yes, you could do that. We don't need this group of 2. though.
Right.
Yeah. Yeah. We'll get to that. The reason you would do that is actually a lot of fun. It's one of my favorite sections. But okay. So then you told me what to circle. Let's see what's the equation? Oops. Sorry.
Would it be B plus?
Well, I've circled 2 of them, so how many terms are going to be? So there's 2 circles. So I know there's going to be 2 terms separated by an or. Right? 2 circles or together. Let's do this circle as our first one. What is this circle? What doesn't change in this circle? B. And what else? C changes. So A and B don't change, right? So this is A and B. Because A and B don't change vertically. Now, does either one of these have a bar? A bar. Do you understand why? Because, yeah, in this column, A is not A, default, and B is 1. A, B. If it helps, so this is the notation that I prefer. An equivalent notation for doing this that is perfectly acceptable is instead of writing the 0, 1, you write the terms explicitly. Then it's a little easier to tell if this is a challenge for you. Either one, right? Because that's all this is saying is the 0 is 1, or sorry, 0 goes to the A and the 1 goes to the B. So this is a little bit more explicit in what we're building out. Okay, so now let's do the second circle. So what doesn't change? C, that's correct. What else? Look over here. So A is 1, correct, does not change. Do either of those have a bar? No bar. Okay. I'm not doing this to make you suffer. I'm doing this because it's important to understand how this happens, right? So F is not A, B, or A and C. So where do these beautiful, annoying K-maps come from? Well, let's do this in reverse. Starting, we'll use this truth table, or sorry, this K-map to build a truth table. You'll always catch me counting up the number of rows to make sure I got it right, because I sometimes miss one. Okay, so what we can do is just start filling in ones. So at 0, 0, 1, we have a 1. At 1, 1, 0, I have a 1. At 1, 0, 0, I have a 1. And at 1, 0, 1, I have a 1. Everything else gets a 0. Right, so I can go K-map the truth table or truth table to K-map, right? That's all this is showing. This is a different way of drawing out the truth table to reveal logically adjacent terms. Because if you look at this and say 1, 1, 0, which is here, and 1, 0, 0, which is here, those don't necessarily look logically adjacent on the truth table, right? But they are, because the only term that changes is B. So this is just a way of revealing logic adjacency. Okay, we'll do more of that in just a minute. You okay if I start erasing? Okay, so now we have 3 variables. What happens if I suddenly want 4 variables? Well, I just label A, B, C, D. Let me make sure this is the way they do it, order they do it in the book. Yes, good. I'm trying to do the book example so you can go back and refresh your mind if you forget how we got from A to B. Okay. You'll notice vertically, I do the same gray code, right? Still need to maintain logic adjacency. Now we start getting into some more interesting circling, right? So we've got a couple obvious big ones, and maybe I'll jump into a little bit of the explanation of why we want big ones, but I think it's apparent, right? So the bigger the ones, the fewer terms that we end up with, right, in each of our or statements. We also end up with fewer overall terms, right? So big circles are better. And so generally speaking, we're going to start looking for the biggest ones that we can find and then fill in smaller circles to encapsulate all the ones that we can. It is possible to have a one that is on its own and can't be circled with another one, in which case, obviously, you're going to have a whole bunch of terms and you just have to live with that. Nothing you can, no shortcuts around it. So, big terms. Well, let's not use this blue, huh? There we go, my green's okay. Right, we've got 4. We've also got 4 up here. And lastly, because there's an overlap, we'll use a different color. I've got 4.
The top row and the bottom row be logically adjacent.
Exactly. So what he just pointed out that I was going to reveal later is I can just erase all of this and do this. And now we've got a big chunk of 8. We like 8 because it really, really simplifies things. And then our other little guy, right, we have to live with the fact that we've only got 2. So that term's going to be a little bit annoying, but these other ones are great. So, who wants to take a stab? Well, just so we're clear, we've got green circle, red circle, red circle. 3 circles. 3 terms, right? Who wants to take a stab at what this big one is?
Not D.
We agree? Does anyone disagree? I'll obviously walk through this, but I like giving the students a chance. Okay, so jumping between this row and this row, what doesn't change? D. Jumping across this row, what doesn't change? Nothing, it all changes. So then we just look at D and nod it. Right? Big 8 term, nice and simplified. Can't go bigger than 8, because if we had 16 terms, it would become logically trivial, right? So the next step up from 8 is 16, and there are only 16. The only way to get a bigger circle than that is all 1s, in which case it's just 1 all the time. Okay, someone else that hasn't gone, want to take a stab at this 4.
AC.
AC. Do we agree? Well, A doesn't change. C is this guy, doesn't change. We know because it's 4, it's only going to be 2 terms, right? If 8 was 1, 4 is 2, and 2 is going to be how many? 3. What is the 3?
C. Would be A naught, B, and C naught.
A naught, B, and C naught. I like A naught. B. Here. B, B, yep. Okay, so we like B, and you like C naught. Okay, I like it. Do we like it? Does everyone follow along with how I got there? Excellent. This is very important. If you don't get it, there are fortunately tons and tons and tons of examples online. Are we okay if I start erasing? Okay. Yeah, we don't want to lose you guys' notes before you're reading. Okay. So I'm going to go ahead and give you guys a problem, and I would like all of you to do it. Okay. A, B, C, F. I would like you to take this truth table, turn it into a K-map, right? This is just going to be a 2x4, and then fill it out and come up with the expression. Give me a couple of minutes. Is anyone at least not, has everyone filled in the K-map? Hopefully everyone has. So I'll start writing that up, so if anyone made a mistake there, they can catch up. Okay, so this one has some obnoxious circles, right? Because we have to circle maybe more than we would like to. In order to get this guy in anything, we're looking there. And then, unfortunately, we have no way of grouping just 3. Did everyone get those circles? How many terms am I going to have? 3 terms. And how many? Well, I should probably come up with better vocabulary for that, but this is an AND gate, right? In each of these, you're going to have 2 terms into those AND gates, right? Just because we're simplifying from there. Who wants to give me the expression? I feel really confident. Go for it.
A dot B, A dot C dot, let's B C dot.
Do we agree?
Yes.
Excellent. Does anyone not get that? No one's willing to admit to missing it? All right. Okay, let's move on to some vocabulary, because everybody likes vocabulary. Okay, so first, most important vocabulary word. If you circle a grouping of things, any circling, that would be called an implicant. Implicant. Then, I like this red. I wonder if it even shows up on the. Yeah, it shows up a little bit. Color doesn't, the circle does. Okay. But obviously, hopefully obviously, this is not a good circle, right? So what we want to start looking for is what we call essential prime implicants. You might just call that an essential implicant. So the idea, the difference is a prime implicant is something that is, it's a circle that's required. Something that you have to do in order to snag one of the ones. It is an essential prime implicant if it's the largest possible that also encircles 1. So our essential prime implicants, let me make sure I'm not missing any of the vocabulary. So you're going to hear each of these blocks. In the book, they're going to reference them as a cell. And if a cell is covered by only one prime implicant, and the specific definition, I should probably read the exact definition. The large groupings are what we call prime implicants, the biggest of prime, and it's essential if there's no other way to circle a 1. So like this one can only be encapsulated in this circle, right? There's nothing else. So this circle is an essential prime implicant because it takes this one and is the biggest circle that I can draw. This is not an essential prime implicant because it is not the biggest circle that I can draw around them. So what we want to start by doing when we're doing these K-maps is look for essential prime implicants. Your biggest ones that will try and cover all of them. Now we can't necessarily get everything we want, and we have a 1, as I alluded to, all by itself. And he's going to have 4 terms because there's no real simplification for him. It is what it is. Yep. I recommend going through, I'm going to go through more examples than going through this. The essential prime implicants, EPIs, are the most important to understand. I do strongly encourage you, so much as assign you to go ahead and read this section called grouping. I don't have page numbers on this. It starts right after figure 7-8. Do go ahead and read that. Make sure you understand what it's saying. Focus primarily on the idea of essential prime implicants. Then what you're looking for, after you get your essential primes, right, these are the ones that are big and cover ones that can't be covered any other way. Then you just start looking for other prime implicants, which are just big groupings. They may not be necessary to do, right? So we could do this and that, and then we're not using any essential prime implicants here. We're not even using prime implicants. We're just having implicants. This becomes a prime implicant, not essential because there are other implicants that can get it. Okay. Don't want to spend too much time on that because we have a lot of, mostly I want to do examples because it's important. Good one. Okay. Get back up to a 4-variable K-map. Okay, let's start by identifying where do we have a minterm that can only be grabbed by a single implicant.
The top row.
Well, not quite. So we can get that grouping or this grouping. So it's got two groupings. I see this one. Right, he's got nobody. I think all of the rest can be got by multiple groupings. So he's the one we've got to look out for because he's both essential and prime. So let's start with him. What's a good grouping for him? Yeah, 4 in the row. That's a great essential prime implicant. Now we've got some choices to make about where the rest of these prime implicants go. Do we have any other groupings of 4 that you can see? Exactly. Outside, outside. See that one? Okay. Any other good groupings? I mean, we're out of 4s. We've got a couple of 2s, right? This is a good 2, and that's a good 2. Right. All of our guys are covered. Made sure to start with the essential prime implicant.
Wouldn't it not be prime because you can do a circle of 2 and a circle of 2?
Oh.
The other one's next to it.
You know what? That's a good point. It is not essential and prime. The prime. This is prime, but not essential. Anyways, I'm not going to go through, unless you guys really want to. Do you guys want to go through this? Getting the F? See some head shakes. All right. We'll move onwards. Okay, I'm going to give you one now that does, in fact, let's use black to start, have an essential prime implicant. I should just make a giant stamp for this type of grid, shouldn't I? Okay, that's interesting. So I had a bit of a mistake that I will now remedy with my definitions. So something I will confess to you, when I learned K-maps, we did not mention essential prime implicants at all. We just said make the circles happen and they would work. This book does it a little differently. I'm trying to make sure I do it. I'm going to make some minor mistakes and I apologize. Last one, this actually is an essential prime implicant. So the definition that they're using is that this, let me grab a different color so it's obvious, is an essential prime implicant. Because even though this one could be grouped just with a smaller one, that smaller one is a smaller grouping of this implicant. So if you break it up into smaller ones, it doesn't count as an alternate one. That's the definition they're using. So previously, this one is as well, because I could group it up into smaller ones, but it would just be a smaller grouping of the larger prime implicant. I apologize for the mistake. Hopefully, I don't confuse you all. Anyways, so I gave this one away. Can anybody identify, there is one other essential prime implicant using our newfound definition. Sorry, let me write up some numbers so you can just yell numbers at me. Actually, no, that's not worth the effort. Okay, in the middle, which, sorry, how many times do I go down?
the groups before in there or on the line? Those four, the first two,
These four?
or this one?
Yeah. So why is this circling an essential prime implicant? Because this guy, right? He can only be grouped in smaller groupings of this big prime implicant. Okay. So then we're going to get smaller groupings, right? Something like here and here. But I think you guys are fully capable of getting these. Let me give you a bit of a trick one that I quite enjoy. So we don't forget that that's what these are, right? I just want to remind you. What's the biggest grouping that I can pull off? Raise your hand with the number of fingers of the biggest grouping that I can pull off. Everyone, hands, everyone, come on. So the answer is 4. Corners.
Whoa. Sweet.
That works. Okay, I'm going to have you guys do a nice 4-variable K map on your own. This one is pretty easy. I know, tons of examples this time, but come exam time, you'll thank me for it. One. Okay. Again, A, B, C, D. I'll write this out for you guys. 0, 1, 1, 1, 1, 0. Did I just recopy it? Ah! That's really funny. I kind of made that one up. So let me find you a different example. So the book example and my head example apparently wanted to be the same. Let's give you a different one. Tell me if I've repeated this one or something awful. No, we've done that one too, haven't we? No, I think it's slightly different.
Slightly different.
Okay. Let's get that equation out. Hammer that one out. Give me a couple minutes. It's just these 2 rows were flipped. I think that's the only difference between the one I did earlier. Just raise your hand if you're done, just real quick, up and down kind of thing if you finish, so that I kind of keep track of where you're all at. Okay. You have a question or you're done? Okay. If you're done, it's just a quick up and down. I'll be good.
Oh, sorry.
Okay, let's start getting some circles. Actually, how many aren't done? You're not done yet?
I'm done, but
You're not sure? And, okay, if you're not sure, are you brave enough to come up and start drawing some circles for me?
okay.
I won't force you if you're not, but if you're up for someone unsure is a great candidate for the circle drawing because it'll help you reinforce the learning. And before you touch your eyeballs or something afterwards, you can use some hand sanitizer. Okay, great. We've got some circles. So I'm going to draw this over with green just because it's a little bit better for the camera. Do you like those circles? Those implicants, as it were? Got everything covered. Everything looks reasonable. There's no reason that you couldn't use this one and that one and this one and that one, right? As also the circles are the same. This is a little bit easier to see, right, when you're not flipping over the map. If someone else would like to come up, would you like a hand sanitizer? I just want to make sure we're sterile. Would anyone like to come up and do the equation?
I have a question.
Oh, you have a question?
So when you're grouping, is there like a particular reason why you wouldn't use like a 3 on that middle row?
Because how do I get 3 out of 2 to the end?
Oh, you don't.
That's why. That's the only reason.
That makes sense. So I'm glad I asked.
Yeah.
The reason of my confusion is because I feel that the equation can be simplified further after.
Oh, you think it may simplify more than that? It can, actually, sometimes. So this is what they would call a simplified solution. It is not the only one, but this type of simplification has a particular kind of benefit to it, which I don't want to jump too far ahead. But this is the simplified term with the most optimal delay path. So if you're trying to design for speed, this is speed optimized. You will see some other tricks. The other thing that's really nice once we get to the next section that you'll see, this type of simplification lends itself really well to designing in universal gates. So converting strictly to NAND gates or strictly to NOR gates. So there's a couple reasons why we would do this. But let's get the F out, the function, get the language, right? Let's get the function written out and see about how further simplifications might happen. Does anybody want to start yelling this at me?
C dot D.
C not D.
CD not,
C D not?
A not, B, C not.
A, B, C.
Sorry, that one seems off. Oh wait, no, okay. And then we got another one.
A, B not, C not.
Yeah.
And A, B, C.
Okay, let me erase this C and D so it doesn't get us confused. Does everyone agree with this? Okay. So, potential other simplifications. There is something that jumps out to me as kind of interesting, but I've seen a ton of digital logic. That this looks suspiciously like it should be simplified, right? Does it? Well, let's do some fun thinking. I think digital logic is a lot of fun. So let's say we have C and D, and think about these two terms. So we're going to only have 4 options of them. if it's 0, 0, what is the we'll call this alpha. 0, 0, what is it? 0, 1? 0. Does this look like something we've talked about?
Exclusive or?
Hmm?
Is it exclusive or?
It's a lot like an XOR with a not on it, isn't it? Right? Because if I drew alpha bar, I would get 1. Oh wait, no, this is XOR. Never mind. This is just a straight up XOR. Sorry, there's another pattern this ends up with XOR as well. So that's why, but yeah, so that's just an XOR. So this whole term, you'd have to check the C and D's to make sure that those match out. But it's just C XOR D. You can end up in situations where it might be like C bar XOR D, but I think this one is just C XOR D. Do you see any other simplifications?
Yes.
What do you see?
A not B, C not, with an S on A, B not, C not. A and B are changing, C is still the same.
Ah, yes. So he's calling out, let me do this in a different color. This term, that term. Let's jump over here. So we have A, B, oh wait, I'm gonna run off of the edge of the world according to my screen. Oh, I've got a little bit of room, we're good. Okay. And you're claiming not A, not C, B, C. So you can factor out the C and the N, A not B, or A B not, right? Now what do we see in here? Another XOR. Right, so there are other simplifications. Now, one of the reasons we might not do that is because an XOR is not one of our universal gates. When we move on to the design, like this is a simpler one if you're building this out of discrete components, right? That could be a very useful configuration. But if you only had a pile of NAND gates, you might not want to try and start implementing XORs using NANDs because that gets a little convoluted. And we will go through a design process of how to take it from this equation essentially directly to a NAND gate design. But it's a good point. Call that out. Okay, so let's do something just a little bit different. Okay, I'm going to leave out the ones because this time we're interested in zeros. So if we take the groupings and we say, first off, we want to ask the question, I should erase these before you begin. Do we have essential prime implicants? Right, remembering this guy is not essential and prime because he can be circled by this and that, and those are not subgroupings of each other. But like this is a subgrouping. I'm really just gonna get rid of this red because I keep wanting to use it and it's just right. That's an important one. Similarly, that's an important one, right? Interestingly, this one can be that way, right, with that circle, or that way. This one can group there or there. So these ones are a little bit wishy-washy on what we actually want to do with them, because I've got multiple groupings. I like to stick, and I imagine most of you will too, on the same side of the K-map without wraparound unless I have to. And then this one is just completely arbitrary, which one grouping you take it with, right? So I take my zeros instead of my ones. And we have the same general concept for F, where we want to start writing equations, but they're going to be different, right? So we're going to have 1, 2, 3, 4 circles. Or probably going to, let's wrap onto another row. But instead of OR gates connecting them together, right? Because plus means OR, not AND. They're going to be grouped like so. So if we look at our first grouping of this big square, I have I have C's not changing and B's not changing, right? So normally, if we were doing ones, it would be B or not C, but sorry, I have to make sure I'm not flipping this. I almost never do the zeros, and there's a design reason for that later on, so I'm making sure that they don't flip the terms, because I think they might. Yep, I was suspicious. If we think back to, what's the term? De Morgan's, right? This is, as I said, and again, I apologize, I don't use zeros, so I almost screwed this one up, but I remembered De Morgan's, and it wasn't quite equivalent. So this is the De Morgan's equivalency. So we take the De Morgan's of the terms, where we're switching the bars on each of those, and we're changing the ands to ors. So that's all this zeros is doing, is this is providing the other output using De Morgan's theorem. So we have to flip those guys when we enter them into the table, or sorry, into the equation. You'll get a feel, right? Because it wasn't like, I didn't remember that this had to be it. I just didn't feel quite right. And as you develop more and more logic, you'll see things that are like the XOR that we just did, that it just feels like it should be simplified somehow, or felt like it was wrong. You'll develop that intuition, but it requires doing a bunch of problems. Who wants to try and throw out the next term for me? Doing this big one.
C or D naught.
Yeah, absolutely. Do we agree? Everyone sees how. Someone else want to throw out the third term for me? Let's use this vertical guy.
A or B or not C.
Do we agree? Got some head nods. We're all happy. All right, last circle. Someone else?
A or not C, D?
Remember the last one? I mean, you'll remember to write it, but yeah. Do we agree with this one? See, several head shakes, yes. Let me check the time so we don't end up going over. We got 15 minutes, it looks like, roughly. Okay, hopefully zeros make sense. They will be on the homework assignment to get some practice. They are generally yet less used. There is an example that I haven't done that you can do, example 7.9. So if you need to go practice some more and with a walkthrough, there are also lots of examples online. There is an important term that I want to get to, which is this idea of what we call don't cares. And all that means is we don't care what it means. The don't care could be that particular state could never happen. Or it could be that in that state we don't care about a particular output, right? So you could have a truth table that had two outputs, F1 and F2, and then like one of these would be something like that. X, it can also be a D for don't care, but generally we use X, right? We don't care what this is. So what a don't care truth table may look like so say I had some functions, say it was 4 inputs, I take these don't cares and throw them where the ones would be, right? So I'm going from truth table 1 and putting it there, and then taking the don't care and putting it there. The nice thing with the don't care is it can either be grouped with the ones if you're doing it that way, or could be grouped with zeros if you're doing zeros, if you're doing min terms or max terms, right? The X can be whichever one you want it to be. So ultimately, if I'm doing min terms, this big square here, perfectly allowable. So don't care, I don't care what they are.
But you don't need to get all the X's.
You do not need to get all the X's, exactly, yeah. So if I have this X floating up by itself, I do not need to circle him. I can just ignore him. I do want to touch on one idea, just a sneak preview. So I'm going to be teaching you 2 ways to do more than 4 variables. One of them I did not learn. One of them I did. I didn't even know the other one existed until I started prepping this class. Because the days where we really care about logic simplification are long gone, right? There was a time when designing logic, you were designing it in discrete components a lot, and you were, I don't know, you had programmable logic arrays that had 20 gates. That doesn't really happen anymore, but you may come across some of these systems in your workings with old system, right? You go out and get an industry job, someone gives you a huge manufacturing machine and they go, we don't know what this data broke, please fix it. Very rarely would you ever want to do logic simplification for a table that for inputs that had more than 4, even rarer that you'd do 5, and even rarer that you would do 6. And you start pressing beyond 6, and you're just gonna let some program do it for you almost certainly. Because it gets really complicated. I will teach you how to do that in case it is ever need done. But I'm not promising yet, but I'm thinking I may limit the exam questions, not the homework, but the exam, to 6 variables. But here's the sneak peek, because I like this lead on a little bit with where we're going with this, is let's say that I had 5 variables. Now this is 4, right? How do I get the fit? How would I ever draw a fit? Well, it turns out that one way, and this is the way that I learned it, and if you have 5 or 6 variables, unless I specifically ask for one way or the other on an exam, I don't care which way you do. You draw a double line. Make another map. And then we make sure that we're logically adjacent across the map. One, one. So we need to end up at 1, 0, 0. 1, 1, 0, 1, 0, 1. 1, 1, 1, 1, 0, 1. Ah, there we go. Right? These are still logically adjacent, and this and that are still logically adjacent. Now this term would just be E, right? And now, if I have these 2 maps, they cross via logic adjacency, that circle works. Just as that circle works. We'll get into some more examples of these next time. We have 5 minutes. Would anybody like to see an example of something in particular that we've covered today?
With terms in the middle, wouldn't they be logically adjacent to the mirrored place on the other map?
These ones?
In the middle. That would be logically adjacent to the mirror image on the other map, right?
Well, you have a 0, 0, 1 and a 1, 0, 1. Those 2 are logically adjacent. In this map, it is very difficult to see that. This way will get you a simplified expression and you may miss 1. When we get to 6, which is actually more interesting, what you do, this is actually a really good catch. Another way of doing this is instead of having these terms here, you draw, let me just start fresh. You draw it the exact same way, and then you imagine picking this one up and sliding that one underneath. And then you have exactly what you're talking about without having to think in mirrored, right? So in this case, logically adjacent is here and here.
It's making it 2-dimensional.
Yes.
3-dimensional.
3-dimensional. And you can build on that, and that's how we get 6 variables, is you draw 4 maps that all stack up on top of each other. And we'll get to that later. There is another way of doing this called map entered variables. And that one extends to more and more variables as long as you can simplify the logic a little bit. But that's what we'll cover next time. Actually, maybe not. Maybe next time is a review. But I think the exam is next week. Have we looked at the calendar recently, anyone? It's either next week or the week after. Actually, I can probably pull up my calendar. Yes, it looks like it is next week. It will cover up through K-maps of 4 variables. It will not have 5 variable K-maps on it. everything else up until 4 variable K-maps. So up until right before I did this is fair game for the exam. We will do a review, I think, next time. And then the exam will be Tuesday, or Monday, sorry. There's a schedule posted online. If it's not, it's screwed up. I have office hours between now and then. Feel free to use them. Try not to panic. I'm doing my best to get your all of your homework graded by the end of this week. Any questions? We're about out of time, so. Yeah.
Is the exam in here?
Yeah, the exam will just be in here. If for some reason, if you catch COVID, say, between now and then, and you're not going to make it, I need to know before the exam, not the day of the exam. Okay? If you wake up feeling sick on the day of exam, I'll try and be forgiving. Please don't abuse the trust, because I have to be trusting, because I don't want COVID. Your classmates don't want COVID. But I would like warning. If you can't give it, it's fine. I'll forgive you. We'll figure something out. But it makes me have to write a second exam because, you know, Gay Chegg and Course Hero and all those other terrible ones that you guys love. Yeah, you guys are dismissed. You're good. Quick answer.
Remind me what a MOSFET does again.
A MOSFET. MOSFET is just a type of switch, right? Draw them like so. Voltage comes in. We know this, the gate. That's all I would expect you to know, because the gate means if I put there are two types of MOS. Let me start here. This is a PMOS. PMOSFET. This is an NMOS. They're switches. NMOS is one here. This turns the switch on. So off in a switch looks like so.
Right.
Disconnected, nothing close. On in a switch just looks like this. So on means current can flow. 1 turns an NMOS on. 0 turns a PMOS on.
So, I'm sorry.
I'm trying to remember if the homeworks have this on there.
That's why I
If
asked.
the homework does, then it will be on the exam. Or at least it's fair game to be on the exam.
So, when I think about this in logic gates, basically buffer inverter.
Yeah, exactly. That's exactly what I drew.
Okay, because it says draw a 3-input NAND using MOSFETs.
Yep. So you have pictures in the book of 2 inputs. So you're going to use that as a template and expand that to a 3rd gate. Right? So a 2-input AND gate looks like so.
Mm-hmm.
A 3-input AND gate is that.
Right.
So we can extrapolate this to the MOSFETs. How do you extrapolate this to the FETs?
Gotcha. And the example of this being a MOSFET is in the book?
Yes. Okay. It has and NOR and the inverter.
Gotcha. Okay. Thanks.
Do you have any of those 3-input NAND gates here right now, or not until the lab today?
Sorry, say that one more time.
Do you have any of the 3-input NAND gate LS7410s with you right now?
I don't. You need one?
I don't need it until the lab, but I built.
If you would like it, we can go grab it if you'd like to wait just a minute.
Yeah.
I just wanted to see it.
I have to sanitize the desk so that I leave, but after that we can walk over and grab you one.
Oh, jeez. Homework's due at 10:30 a.m.
Is it?
That's what this is.
That's like
This is the first one. This is the only one.
they used to all be that way. I extended it to midnight because the way the previous professor did this course, he made it due before class. I've been a little bit more lenient because we live in the land of COVID, and I think leniency is fair.
Right.
Is it due tomorrow or when?
It says today at 10:30 a.m. All the other ones are midnight.
Okay. I will look at. I assume you haven't turned it in yet.
No, I was waiting for that question. I'm almost done.
I will expand it to midnight.
Okay. Awesome. Thank
Send
you.
me a message.
I will.
Canvas so that I don't forget to do that.
Thank you. Appreciate it.
Yep. started your programming thing?
Yes, I am pretty much done. I only
That was all the dust. Oh, shoot. I did not end this call.